All right, so we're going to look at related rates of change. So this is lecture 40 of Specialist Maths. Some of the prior knowledge in order to understand this would be differentiation techniques, the chain rule, parametric differentiation, implicit differentiation, and a strong understanding of geometry of shapes, so things like area, volume, surface area, and so on. All right, the key concepts we'll actually cover in this video will be related rates, and we'll sort of demonstrate that through an applied example. And then we'll look at related rates for parametric equations, the gradient at a point on a parametrically defined curve, understanding related rates through composition, and the application of related rates with parametric equations. So let me maybe explain this picture because it seems a little bit random. What we're going to do is we're going to think about a golf ball pyramid. I'm not sure if anyone's into golf here, but sometimes you go to the driving range and they have these golf ball square-based pyramids. And what we're going to do is we're going to start to think about, if you were to imagine that golf ball pyramid growing uniformly, how would the volume change with respect to time, the side length, and the height of the pyramid all change with respect to time. We're going to start to relate those concepts together. So hopefully you're up for it. I think it'll be interesting. So let's jump into it and think about that applied example. So we're going to look at related rates. And yeah, firstly, here's our pyramid. Give us a spin. Maybe a bit quicker. There we go. Too quick. Here's our pyramid and golf ball pyramid, quote unquote. And what we want to do is we're going to think about the different rates of change. So if we just start to define some of those rates, we could say dV dt would be the rate of change of volume with respect to time. ds dt would be the rate of change of the base length with respect to time. dh dt can be the rate of change of height of the pyramid with respect to time. Okay, and let's not leave you wanting more. There's the pyramid growing, right, as time passes. Okay, now in order for this problem to sort of make sense as we try and understand this concept, we have to assume that the face angle is maintained at 60 degrees as the pyramid grows. So this angle here is always 60 degrees. We're basically not getting things like this going on, where the angle's changing, because that makes things a lot more complicated. And we just want to consider a situation where it's growing uniformly like that. So think like when you paste a picture into Word and then you grab the corner and everything grows in proportion. But if you grab one of the sides, things don't grow in proportion. So we're maintaining that angle at 60 degrees. And obviously not a good assumption, because if you were filling a literal golf ball pyramid in the real world, it wouldn't grow uniformly. I don't think it would grow from the top, and it'd be very different. But this is why we love maths, because we can sort of build in our assumptions a little bit. All right, so if we take this triangle in here, we can see that it's a right angle triangle. And so we've drawn that right angle triangle here. Now clearly that's the height. And S on 2, well, we know that it's a square-based pyramid, so this length here is S. So this is clearly half that length, so that's S on 2. And just from some basic trig, we know that tan of 60 degrees, the tan of this angle is equal to opposite over adjacent. So it's going to be equal to H over S on 2. And so what we might want to do now is rearrange to find H in terms of S. So we're going to get H equals S root 3 on 2, if you just rearrange that. Okay, so that's good, because now we can get everything in terms of S. And when I say everything, what I mean is we can think about the volume now in terms of S. So let's think about that. There it is. So the volume of a square-based pyramid is 1/3 S squared H. And now just a bit of geometry briefly here. Remember, a square-based pyramid is a tapered solid. So tapered solid is any three-dimensional object that finishes in sort of an apex, like a pyramid or a cone. And so that has that factor of 1/3 there. S squared is the area of the base, right? That is a square base pyramid, so that's the area of the base. And H is the perpendicular height, so that's that height there. And recall that H equals S root 3 on 2, just from before, right? So we can now write the volume of the square base pyramid in terms of S only. So if we change this H to be equal to this business, then the volume of the square base pyramid in terms of S is S cubed root 3 on 6. Okay, And so what we can do now is you can actually start to relate the rates of change together by the chain rule. So if you look at dh dt, so if we were interested in how does h change, how does the height change as time passes, we could say by the chain rule that dh dt is equal to dh ds by ds dt. And yeah, we know that dh ds is just root 3 on 2, because if you differentiate this, the s just drops out. And that should make sense. Just think about what that actually means. How does the height change as s changes? Well, it changes constantly because the ratio between h and s is fixed. As we said before, we're not getting any changes in the angle. So this should make sense that this is a constant. So dh dt equals root 3 on 2 multiplied by ds dt, but we don't know what ds dt is yet based on what we've learned. But when we get given a problem, we will know what ds dt is and we can sub that in. Okay, so we've related dh dt to ds dt through this formula. Now let's see if we can relate the volume to the change in volume to the change in side length. So that's going to be dv dt equals dv ds by ds dt, again by the chain rule. And so we're going to get this. In dv ds we know, because remember we have v in terms of s. So if we differentiate this, we get s squared root 3 on 2, again by ds dt. So that's again another application of the chain rule. And so now what we've got is we've actually related all of our rates, because you notice ds dt is in both of these equations. So with the relevant rearrangements, you could relate all of those rates of change together. And again, big picture stuff here, it should make sense that all those rates of change are related. You're changing s, which is going to change h, which is going to change v. So it should make sense that we're able to relate all of those rates of change together. Okay, so let's see how this might apply to a problem, right? So here's our problem. And maybe that's a bit hard because the answer's there, but I don't know, maybe pause it and give it a go. So the golf gods stack golf clubs in a square-based pyramid at a driving range. The pyramid grows uniformly, maintaining a fixed face angle of 60 degrees, as we said, between the slanted triangular face and the ground. At a certain moment, the side length of the base is increasing at a rate of 2 centimeters a second. So that S is increasing at 2 centimeters a second at some point. The base side length is currently S equals 30 centimeters. So it's 30 centimeters when it's increasing at a rate of 2 centimeters per second. Okay, so the question we might be interested in is what is the rate of change of height of the pyramid at that moment? Okay, so from before we saw that dh dt equals root 3 on 2 by ds dt, but now we know what the s dt is. We know that the rate of change of s of the side length with respect to time is 2. So we get that dh dt is just root 3, which is 1.7 centimeters a second. So when the side length is changing at a rate of 2 centimeters a second, the height is changing at a rate of 1.7 centimeters a second. Okay, which is pretty interesting. And so now we can think about the volume. So how's the volume changing with respect to time? Well, we know from before again that dv dt equals s squared root 3 on 2 by ds dt. And so we also know that s, at the moment when the rate of change of the side length is 2 centimeters a second, s is 30. So we get that, we sub 30 in. So we get 30 squared root 3 on 2 times 2, which is approximately 1,559 centimeters cubed a second. So when the base side length is 30 centimeters of our golf ball pyramid and it's changing at a rate of 2 centimeters a second, the volume is increasing at a rate of 1,558 centimeters cubed a second. All right, so that's how we've been able to relate, the height, the side length, and the volume all together using related rates of change. Okay, so what we might do now is, and I should just say before we move on, like you can generalize that, those findings, right? We've obviously used, well, there's a challenge for you. We've obviously used the volume of a pyramid here, but by the chain rule, it's the key idea here. We're able to relate those rates of change to one another, so you can apply that to many problems. All right, let's move on to parametric equations and related rates when you get given a parametric equation. So let's imagine for a moment that we can, well, let's firstly recall parametric equations. So parametric equation is basically this idea that you've got some coordinate in space and the x position is defined by some function of t, and the y position is some other function of t, some other parameter t. Okay, let's just think with a solid example for now. You might recall from parametric equations that the unit circle can be defined as the x value being x equals cos of t and the y value being y equals sine of t. And so if we take this point and we trace it out, what we can actually get, so this point here is currently t0. If we trace that out as t changes between 0 and 2 pi, we'll see that it traces out a unit circle, right? And then we've got a tangent there to sort of help us visualize things. So we end up with that situation. And so what we might ask ourselves is, okay, well, how can we find at some... So the question is, how can we find the gradient at a point on a parametrically defined curve? So for example, if we were at some point in space, or some point on the unit circle in this case, how could we find the gradient at a point on that curve? Well, what we do is, if we just jump straight to here, it should make sense. We said that the derivative of y with respect to x, so the change in y with the change in y over change in x is equal to dy dt over dx dt. And that, again, should make sense. It's like the y, the vertical position of that point is changing with respect to time, some amount, and then you divide that by the horizontal change with respect to time. Even though it depends on another parameter, that's fine. You're still able to find dy dx by taking dy dt over dx dt. And so, just to really make it concrete here, and I encourage you to get out a pen and paper, we've got the unit circle. Again, cos of t, sine of t is how that's parametrically defined. And then I know that pi on 4 is approximately 0.79 radians. As a decimal, it's 0.79, which I know is 45 degrees. So if I was to draw a line from the origin to that point there, I'd get an angle of 45 degrees there. Okay, and so I know that a line perpendicular to that would be this tangent here. We know that has a slope of -1. And so I encourage you to maybe use that as an example of applying the gradient at a point on a parametric curve, but I'll leave that as an exercise. So again, just to reiterate, this point from here to here would have a 45 degree angle, or pi on 4 radians. We know that that would have a slope of 1. It would have a gradient of 1. And so we know that a line perpendicular to that would be -1, because we know all about tangents and normals and all that stuff. So again, yeah, just to reiterate, what we could do is you could apply this. You could find dy dt at t equals pi on 4, and you could find dx dt at t equals pi on 4, and you should get -1 as your answer if you apply this formula. Okay, now the next minute or two, if you're not super interested in it, you can skip past, but this is how I wanted to understand it, and for my own sanity. This is fine if you understand that, that's all good, but when I think of the chain rule, I think of composition of functions. So I really wanted to understand related rates of change through a composition of functions. So if, again, and just bear with me here if you're interested, if you've got given some function x equals f of t and y equals g of t, you're going to assume that dx dt is not equal to 0, as we said before, and that f is locally invertible. So what that means is we can isolate t. So if you look at x equals f of t, if it's invertible, then we can take f inverse of both sides and we'll isolate t. So we'll get t equals f inverse of x. Okay, so if you're comfortable with that step, we can start to see how a composition of functions will arise out of this. Okay, so we know t equals f inverse of x. So we know y is equal to g of t, just by the way it's parametrically defined, but we know t is f inverse of x. So we know that y equals g of f inverse of x. And now by the chain rule, because we can use the chain rule, we've got a composition of functions, we can say, all right, dy dx, the derivative of this thing with respect to x, remember the chain rule says take the derivative of the outside, leaving the inside the same, and then multiply by the derivative of the inside. So let's do that. We're going to get g dash of f inverse of x That's sort of taking the derivative of the outside, leaving the inside the same, and then multiply by the derivative of the inside. So we're going to get f inverse, or we're going to get the derivative of f inverse of x. And if we write it in a slightly different notation, we can see that this term here is just dg dt. It's g dash of t, because remember, f inverse of x is t. So this is just dg dt. And this here, remember, f inverse of x is just t, so this is just dt dx. Okay? But we also know that from sort of reciprocal things we've learnt about derivatives, that dt on dx is equal to 1 on dx dt. And so we get the same rule, but doing it sort of through understanding it as a composition of functions. So we get dy dx equals dy dt on dx dt, which is the same rule that we had here. You're probably wondering, why did that g change to a y? But remember, g of t is equal to y. So this can be replaced with a y. So yeah, a little bit confusing, I think, to understand it as a composition of functions. But if you're satisfied with this explanation, that the gradient at a point on a parametric curve is just the change in the y values with respect to that other parameter t, divided by the change in the x values with respect to that parameter t, then you can find the gradient on a point of a parametric curve. Okay, so I think it'll make more sense with an example. So let's look at an example, and why not stay on the golf bandwagon. So just give me 1 sec to, oh, there we go, that'll do. Just wanted to get rid of that. So a golfer hits a ball off a tee, and its position after t seconds is given by x of t equals 60t cos theta, and y of t equals 60t sin theta minus 4.9t squared, where x of t is the horizontal distance in meters, and y of t is the vertical distance in meters, and theta is the launch angle in radians. All right, now we're going to suppose that the ball is hit at an angle of theta equals pi on 6. So it's hit at an angle of 30 degrees. At the instant the ball has traveled 30 meters horizontally, its height is approximately 15.7 meters and increasing, so it's on the way up. What is the rate of change of the ball's height with respect to horizontal distance at that moment? And so what we can do is we can actually graph this. And so let's see how long it takes our golf ball once it gets launched to come down, and we can trace it out. So we get something like this. So remember, the x-coordinate represents the horizontal distance, the y-coordinate represents the vertical distance. And you look there, I think this is just interesting in itself. It takes about 6 seconds for the ball to come to rest. And for any golf people out there who might be interested, it took 6.12 seconds for the ball. That's how much hang time the ball had, how long it was in the air. I think that's pretty interesting. Okay, but our question is, at the rate, what's the rate of change of the ball's height with respect to horizontal distance at this moment, which is when it's 30 meters horizontally and 15.7 meters vertically. And so pause the video based on what you've just learned about parametric related rates of change, see if you can work it out. But here is the answer. So let me just step through it. So again, our function x of t is our x-coordinate is 30 root 3t when we know that the launch angle is pi on 6. It simplifies to this. Similarly for y of t, when we know theta is pi on 6, we get this value here. All right, differentiate both sides with respect to t. So you get dx dt equals 30 root 3, dy dt equals 30 minus 9.8t. That's just differentiating this. Okay, use the chain rule. So from before, we're going to apply what we just did. So dy dx equals dy dt over dx dt. So that's 30 minus 9.8t divided by 30 root 3. And now what we want to do is we want to solve for t when x is 30. So when x is 30, we're going to sub the left-hand side here as being 30. So we're going to get 30 equals 30 root 3t. Rearranging for t gives us 1 on root 3. So that tells us how long the ball's been in the air when it's a distance of 30 meters horizontally. Okay, and now we know that because that was the only thing we didn't know in our formula. We didn't know what t was. Now we know t. So we're going to sub that in. So you're going to get this messy thing here. You're going to get dy dx equals this. Simplifies to this. This fraction here is approximately 5.66. So you get 30 minus 5.66 over 30 root 3, which is this, which is approximately 0.469. And so our final answer for dy dx is 0.469. And so what that means in practical terms is for every meter that we change horizontally, we get 0.469 meters vertically at this moment here, at that instantaneous moment there when it's 30 meters horizontally. And it's unitless because it's a change in vertical height divided by a change in horizontal height, which is meters divided by meters. So it makes sense that it doesn't have any units. And so, yeah, at different points, dy dx will be different. And you can imagine, for closer to the t, you would have a larger change in y over change in x because, it's taking off. And then at the top, you would have dy dx being 0, right? So hopefully you found that interesting. If you did, please give us a thumbs up. Let us know if you need any private tutoring. Hopefully some of this stuff is making some sense for you. And yeah, reach out if you need a hand with anything, and good luck with all your studies. I will talk to you soon.